All right, I was telling the others, we've been doing schedule for fall, and it was due today, and my work study student was helping me get the things entered, and we got it done with 7 minutes to spare. So I felt real good about it, and I said, well, I have time to eat my apple. I started eating my apple, and then I saw this note to myself to email this woman physics syllabi that she needed before she could register. And I thought, I got to do that before class. So I started typing one-handed because I was eating my apple to send her the email. What's that? No, I finished. Okay, but right about the time I was about midway through the email, the phone rang. And my work study student picked it up, and he was trying to put her off. But I finished the email and said, I can take it. So I did. And she was wanting to set up time for advising tomorrow evening, and had to work out a time for that. So, and then where my office was and all sorts of stuff. I thought, I'll never get to class, so I'm just now here. So,
we would have waited
at least 5 minutes. Yeah, I got it. Okay. So, okay. Other announcements, let's just talk about how we're going to finish up the term. Today we'll finish chapter 6 with no sweat, and we'll start chapter 8. I'll say sweat, but whatever. Okay, start chapter 8, and then at 3:45 we'll do the last lab for chapter 6, which will be electromagnetism lab. And we'll actually be kind of all over the place, mostly down in 259, but we'll wander around the halls a little bit, not too much with that. Okay? Then after that, and the lab probably won't take the full 2 hours, but it's a fairly lengthy lab. It's 3 pages, but it goes pretty quickly. Okay, then here's Mason. Okay, you didn't bring any more with you, huh? Okay. Okay. Now, after, so on Thursday, we'll continue in chapter 8. Don't know if we'll finish it quite or not. We'll only have 2 hours of class. Well, I don't know. We'll see. If we get far enough in chapter 8, we'll have 2 hours of lab. If we don't, we'll just continue class. So it'll be 2 or more hours of class. But the last 30 minutes of class on Thursday will be your chapter 6 test, the chapter we're on now, electricity and magnetism. Okay? If we get far enough in chapter, the odds are we won't be finished with chapter 8 in time, so we'll probably then on next Tuesday, a week from today, if we have more chapter 8 to do, we'll do. If not, we'll do the last lab, which will be chapter 8 lab. And if we have finished chapter 8 on Thursday, then we'll have the test on chapter 8 on Tuesday. Okay. Then it's up to you if you want to take the final or not then. Technically, your final, you know when your final is really scheduled?
You told us it was on Friday.
On Friday of next week. And I thought, no way, okay? These guys are, they may even have other Friday classes, and so their finals for those classes are then. So I said, we're going to have it on Thursday. It will be technically it's next Thursday. If we finish everything in time on Tuesday and you want to take it on Tuesday, I'll let you do that. Okay. But I think we will probably be through. But
So we got one more test on the final, right?
we have we have chapter 6 test. The last, we have, in order. The last lab in chapter 6, that'll be today. The test on chapter 6, that'll be Thursday. And probably the lab in chapter 8 will be Tuesday. And then if we have finished the chapter, I think we will have finished chapter 8 by the end of class on Thursday. If we have finished, then the test on chapter 8 will be Tuesday. Okay? So we'll conceivably have the lab on chapter 8 Tuesday, followed by the test on chapter 8 Tuesday. And then if you want to do your final, you can. If not, I will be here Thursday and administer the final on Thursday. So you got lots of options. Have you done the student course evaluations?
Yeah.
Good, fantastic. If you haven't, please do those before the end of the term. But if you want to wait till closer to the end, that's okay, but please don't forget to do the student course evaluations. All right, any questions before we get going today? And by the way, let me say this also, okay, because this class, technically the last day of class is next Tuesday, not Thursday like it would be for a full-term class, but next Tuesday, 1 week from today. That's technically when your papers are due, okay? I'd love to have them sooner, so if you can have them to me today, tomorrow, Thursday, Friday, or Monday, any day ahead of Tuesday will be fine, but drop dead day is Tuesday. Okay, that'll be fine. Just get them by Tuesday. Also Tuesday, at the beginning of class, I'll be returning all your labs and all your tests. That means any labs or tests you haven't completed or done, you can't do it Tuesday is the last day for that. And you have to have them done, turned in to me by the beginning of class. Now, if you want to go to another room and finish a test, you can do that. But we'll be having class in here. You may be missing a lab. So it just gets messy. So, and I think we decided, we talked about anyway, maybe having pizza on Tuesday as well. Everybody okay with that? And have that maybe right at 1:15. That way it'll count for lunch, or you want to have it at the end? Say again? I can't hear. At the end? The pizza will be getting cold then, by then, because I have to get them before class.
You just stop class an hour earlier.
Oh boy, he's generous, isn't he? Okay.
That wasn't even me.
So you wouldn't rather have that for lunch? Okay. I just figured at 1:15, because y'all are coming right out of another class, aren't you?
I am.
So sometimes you don't have really much chance to eat. I thought that'd give you a chance to eat. But we'll talk about it Thursday. Okay, we got another day to spend on that. But I will be returning all papers, except the research papers. I got to hang on to those because they periodically ask for samples of student writing, so we have to hold those for at least 3 years. But the other tests and labs I want to return to you. They will be returned next Tuesday, so please get anything done you're going to do before Tuesday. And that's the last day to turn in the research paper without losing points. So, any other questions? All right, now this is the slide we left off on. I think we had already done this one too, right? Yeah. But we hadn't done the example 611 on this page. This is page 166. So let me find a slide that I can write. Here we go. That's why I was on that slide. Okay. Example 611. 3 resistors with resistances of 12 ohms, 8 ohms, and 24 ohms are in a series circuit with a 12-volt battery. Let's just back up here. Let's go. There. This is on page 166. Okay, here we have it. 3 resistors. Now these are light bulbs. Probably not these resistors. Just imagine these are resistors rather than light bulbs. Okay? So this is let me get my pen darkened. Okay. This is a 12 ohm resistor. I won't call it a lamp, it's a resistor. An 8 ohm resistor. And a 24 ohm resistor. Okay? Well, let's see what it says. In a series circuit with a 12-volt battery. This is a dry cell, no way that's 12 volts, but we'll just imagine this is a 12-volt battery. Okay. The first question they ask here is, what is the total resistance of the resistors? You're right on the money. What would it be? 44 ohms. Because these are in series, you add the resistances together. Because this battery has to supply enough current at enough voltage to go across that one, and across that one, and across that one, so the resistance adds 44 ohms. Very good. The B part. The B part says how much current can move through the circuit. How would you determine that? Yes, current I is equal to voltage V divided by resistance R, and since we're told the voltage is 12 volts and the total resistance of 44 ohms, I can't write my symbol, there we go. It's not that funny. Okay, now if you got a calculator, what do you get?
You want the electrical answer or you want the
Decimal.
science answer?
Decimal answer is fine.
Two different answers.
They're the same answer, just expressed differently.
Okay. You 0.27 amps in here, but
0.27 amps. What did you get? 270 milli?
milliamps.
Huh?
272 milliamps.
Yes.
It's the same number, it's just
Right.
that would be incorrect in electrical class.
What, 272 would be, or 0.27?
Right, is that.
Okay.
They want you to,
Give it in milliamps
well, give it, if you can.
without a
Some
decimal.
kind of notation, don't leave it like that.
Okay. Well, either would work with me. I'm not picky. As long as it's the right answer. Both of those are the right answer. Okay? Now, the C question is, what is the current through each resistor? It's the same, absolutely. The current that leaves here has to go through there, has to go through here, has to go through there, has to go through there. The current can't be changing there, okay? Same current goes everywhere. So that 272 or whatever it was, milliamps are points. The voltages are different. You're absolutely right. And how do you know? Because the current and resistance differ. So the voltage here would be 12 times 0.27. The voltage drop here would be 8 times 0.27. Voltage drop there would be 24 times 0.27. And if they don't add up to 12, you've done something wrong. You got it right. Perfect. Very good. So I didn't write the C, but it's the same current through each. Okay, good deal. Now, there is a nice little blurb, the top of page 166, where that question was, and that is on blackout reveals pollution. Back in 2003, I guess a few of you were born then, August of 2003, problems in a huge electrical grid resulted in power plant shutting down across the Ohio Valley, and a massive electric power blackout affected some 50 million people. None down here. Southeast was fine. We got plenty of power. But they didn't. And this was scientists from the University of Maryland took advantage of the event to measure different levels of atmospheric pollution while the fossil fuel power plants were shut down. And they took as many air samples as they could. And it's a pretty interesting little article. There's some questions there for you to think about. If you wanted to follow up on that and write your paper on that, that would be fine, but it's still pretty interesting to read. Across the page, on page 167 or thereabouts, is a closer look at solar cells. A pretty good article here. I mean, it's pretty long, and it goes into a lot of good stuff about solar cells. Now, if you're writing on solar cells, this cannot be your source, but this could give you a lot of good ideas. You go find the source outside the book to write your paper. Okay. Now we move to example 612, and I think just like we did, the total resistance was the sum of the three resistors, so we had already done that. All right, and resistance is in circuit. If you have parallel resistors, and here we have, it says, assume the three resistors in example 611 are now connected in parallel. So reviewing that, that's an 8 ohm resistor. We'll put that up here. A 20, wait, I'm sorry. One's a 12. Okay, I put it in the wrong place. 12 ohm resistor, 8 ohm resistor, and a 24 ohm resistor. I didn't put it in the right order, but it's fine. Okay? Same 3 resistors, but now we put them in parallel. Okay? What is the combined resistance, or what I call the effective resistance? The book calls it total resistance. Second? Okay, equivalent resistance. Another way to express it. How do you do that? Does anyone recall? That's it. So here's how the book says it, and it's one way to express it. 1 over RE, equivalent resistance, is equal 1 over R1 plus 1 over R2 plus 1 over R3. A little more math involved in this one. So what would this be? 1 over 8 plus 1 over 12 plus 1 over 24. Now how would you add those 3 fractions together? Common denominator would be 24. So what would it take to make that first denominator 24? What do you have to do to get that? Multiply by 3. So if you multiply the numerator by 3, that becomes 3 24s. To get the second denominator to be 24, what would you have to do? Multiply by 2. So you multiply the numerator by 2, and that gives you 2 over 24. And the third one? 1 over 24. It's already got 24 as a denominator. Add those together, and what do you have? Not quite. 6 24s. Okay. Which you could reduce to be 1/4. But that's 1 over RE, so that makes RE, flip it, like you said. And what do you get? 4 over 1, or 4 ohms. The effective resistance is 4 ohms. Or you can use it on your calculator. It does it just as nicely. You just don't appreciate the math of it as much. Okay, so notice here. You keep adding resistances, and what do? You drop your effective resistances. It doesn't seem like that makes sense, but it truly does. Okay? And partly because of the next couple of questions. So there's the first. What's the combined resistance, or the effective resistance of these 3? 4 ohms. Okay? Now, it says next, what is the current in the overall circuit? That's the total current that leaves and comes into the battery. This current down here. Well, what you have to do is figure out how much current goes through this one, how much goes through that one, how much goes through that one, and they split going out and come back together coming in. So
you can write what you already know. You can write 12 volts for each branch.
Okay, and it's 12 volts across each one. That's one thing I didn't write down. This is a 12 volt resistor here. Okay, so.
You can calculate your own law for current.
Okay, and what would that be?
Each branch.
Yeah, well, what's the Ohm's law for current? I is equal to V over R. So the first one would be 12 over 8, which would be 3 halves, isn't it? Yeah, 1.5. 1.5 amps. This one would be 12 over 12 would be 1 amp. And this one here would be, no, 12 over 24. 0.5 amps. And you add those together and you get, second? Yours is right. 3 amps, very good, 3 amps. Okay, so the total current is 3 amps. Remember what it was, the same 3 resistors in series? 0.27 amps. Now it's up to 3 amps, more than 10 times greater current. Okay. We could have done that as well. V divided by effective resistance would be 3. 12 divided by 4, 3. So there's two ways usually you can check these things. And that gives you 4 amps total resistance. Okay? Total current, yeah. What is the current flowing through each resistance? And we just did that. 1.5, 1, and 0.5. In a series circuit, the voltage is divided, and you add those up, and you add up the resistances as well. In the parallel circuits, the current is divided and then added back up.
You got the Kirchhoff's current law in there.
Yeah.
Same current you got going into a
Node or a
branch.
yeah.
It's the same current coming out.
Right. Exactly. So you got 3 volts going. 3 amps going in here, half an amp going here, 1.5 going there. Okay. At this one, you got 1.5 going here, 1 goes there. 2.5 going there, 1 goes there, 1.5 goes there, and then coming back, same thing. Yeah, absolutely right. Kirchhoff's, do they call that? I call them nodes, but they usually don't call them current law. Okay, but there's another one that sometimes they use, and I can't remember. It's junction. Kirchhoff's junction law, and current law, same thing. Then the loop law is the voltages around the loop. This one would be pretty simple. Okay, now I believe that answers all the 3 questions on that one. So I think now we're ready for household currents. And there was the formula we used. I'll erase my scratch so you can see just as Ryan comes in. All right. And that's exactly what we did. 1 over R. I like to call it effective, okay? 1 over R effective is equal to 1 over R1 plus 1 over R2 plus 1 over 3.
Well, I do put R total by itself over there.
Right.
And I write all of that you got on the left and put a line across all of it and 1 on top.
Right, okay. That works too. What you do is reciprocate both sides, right? Right. Yeah. And your calculators will do it, yeah. Okay. Any questions on either one of those examples? All right, good deal. Thank you. What's that? I keep it in the scrap. Okay, thank you. All right. Well, we be here tomorrow? Okay, see you then. Okay. Okay. Let's talk about household circuits. This is where we live most of the time when we're not at work. In our household circuits, the combination of series and parallel circuits. Generally, very few things in series. In this room, would anything be in series?
No.
What?
Not the light.
The lights wouldn't be. They're parallel.
The receptacles, it depends on how they wire. You can wire parallel. But
Yeah.
if you do them in series, and that receptacle go bad,
Everything else would do.
Parallel would be the best way.
The only thing that really is in series is the switch has to be in series with the volts, right? Otherwise, if it could skip that, it couldn't. So, yeah. Say again? Yeah, I know, the resistances, yeah. So that was, yeah. The switch has to be in series with whatever it's going to cut on and off. Otherwise, it doesn't do any good. So, when they say combination series or parallel circuit, mostly it's your switches in series. There's very few things other than that are in series. Most things are parallel. The light fixtures in the room are parallels because you turn on the switch. If I take a bulb out of one of those, it doesn't shut down all of them. The others have pathways. Appliances are usually in parallel. Same voltage or plate available to each one. And the problem is if you get more and more, just like we were seeing before, more and more things on one parallel circuit, that voltage there that's usually fixed has to supply more and more amps to cover every one of those resistances, and the amperage keeps going up. That's why you have circuit breakers or fuses. And the first house we lived in, the one we rented when we first came to Birmingham, it has an old fuse box. I had to, huh? No, don't do that. Boy, did I hear an electronics person say that? Nancy, okay.
Well, people did.
Oh, I know they did, and people burned down their houses too. So, but we had, it was so bizarre. They said the kitchen has been updated. The rest of the house still wasn't. The kitchen has been upgraded, and sure enough, they had receptacles all around the kitchen. We thought this is great until we happened to be. Karen turned on the coffee maker. At the same time, she turned on the microwave to heat something, and right about that time, the refrigerator kicked in. The compressor came on. There it went. All they did was put more and more receptacles in parallel on the one original circuit. Yeah, and but they didn't then. Okay, not in this old house. So we invested in the fuse company and kept Big B in business because that was walking distance. I kept going over there to buy more fuses, buy the packages. Okay, because they were always. It was a long time ago.
I changed my panel from, that's the first thing I did when I got in there. They had a glass fuse panel in there, and I remodeled my basement, and it was just enough circuits. So it really, the glass fuse panels were really overloaded. What they were doing. They had too many circuits under one fuse. You pull one fuse, a lot of stuff will go off.
Yeah.
So it wasn't set up, and you didn't have no room for no addition.
Right.
I changed out that whole panel.
Right. You almost had to. So they're done so that you do prevent the overloads, which was good that it was preventing them, because you could never control when that refrigerator compressor was going to come on. When it did, if you had anything else on, usually there went the circuit. So, and by the way, those fuses had to be in series, just like the switches do, because you had to have all those going through. So, and this is, of course, AC, and that's why they show going to ground. You don't usually show that in DC, but you can. I mean, it could be shown. Okay, and here we have one circuit that has a light on it. Now this is, that light is in parallel with that switch and that switch receptacle and that one and that one and that one. This has a toaster oven, a can opener, a radio. Which of those is going to draw the most? The toaster, big time, because anything producing heat.
How many watt bulb that is?
Well, if it's going to outpull the toaster, it's going to be a mighty bright bulb. Okay.
Floodlight.
Yeah, a floodlight, a big floodlight, as in a, what is that, helium arc or something like that, I don't know. So, these are all parallel, but one switch. Now, this would not be a wise move here. That one switch is only for the light. Only for the light, that's right.
The power is just going to
Everything else is going,
We're using the
has
same,
going to go, yeah.
same circuit, same hot to power up that whole circuit.
Right. The switch is only for the light, right? And if all those came on, you probably are still not in any bad problem.
You probably get away a bedroom like that, doing that.
Yeah. Now, the bedrooms in that old house we were at generally had one receptacle per bedroom. Big old nice bedrooms, but only one plug. Okay, you got one pair of plugs, And so what you wound up doing is running drop cords around the floor all over the place, which then you had to be careful, is the drop cord rated to carry the current that you're doing? So there were all kinds of good problems. And of course, there's no air conditioning, and one bedroom had a window unit. So that was, and I think they did run a dedicated circuit for that one, but that was not the way to wire a house. Of course, it was a really, really old house. Had a lot of character and charm, and also a few places you could see through the basement walls, but never mind that. It had a lot of character and charm. Okay. Household circuits, that's typically how they go. Now, I can remember before there were plugs like this. What is special about this plug? It's polarized. What tells you it's polarized? Yeah, this end is bigger than that one, so it will only go into a receptacle that way. This old house we were in, no 3-prong plugs and no big receptacle here. You know, they were all, everything was the same size.
On your refrigerator, you had to buy this other plug and screw the ground to the screw in the plug. Yeah.
Okay, very good, safe move, right?
I mean, it works.
It works. We hope most of the time. Yeah. So there have been improvements since the old days when all plugs were just 2-prong plugs and neither one of them. This is polarized, so your load is coming this way and this one's going to ground. For me, that just seems backward. It seemed like the big one would have the load and the small one going to ground, but it's not. It's the other way. So the potential difference between 2 wires in each device, energized load carrier this size and grounded or neutral wire that way. But other plugs actually have a 3rd prong on them. This one doesn't appear to. I can't see one. What is the 3rd prong? Another grounding wire. This is going to ground for the circuit, but that is a grounding wire that is something.
Actually, one of those is hot, no, and neutral.
Yes.
But in the panel, they got it bonded to ground.
But yeah, exactly. Okay. So that's how they do it. Now, other circuits have one more level of safety besides the 3rd prong. Yeah. Ground fault interrupt. GFI. Yeah. FI. Okay. I'd always heard it called ground fault interrupt. So GFI, the GFCI. Okay. This is it. Ground fault interrupt. And what that does, where do you usually have those?
Around the countertops or the sink
Okay, wherever you have water, bathrooms and kitchens near the sinks, and also most of your outside receptacles where you can get rainwater in them. Because what you don't want to happen is you become part of that grounding circuit. You want it to be the grounding circuit and not you. And I don't know if you remember the old.
They got GFI breakers now. Some of the GFI is made on the breaker now.
Okay, I didn't know that. Okay. My younger brother works for an electric power company. He hates GFI. As soon as they put them in at his house, he takes them out. I don't know. Something wrong. He says they just go bad too frequently, or something like that. I mean, I don't know what his reasoning is. He said, "Don't touch mine." You know, so we'll live with it. Yeah, I think they pop and he doesn't like it. He has to reset it. Now we have one at our house that we currently live in that is for an outside circuit. Well, no, this is maybe what you're talking about. On the breaker, it's an outside circuit, but man, that thing, just about every rain, if you're doing anything with that, any rain is going to kick it out because something gets shorted, and I'm glad it kicks it, but it's a pain in the neck because then you have to reset your timer and everything for your outside light. Okay. So there's some of the elements of home safety. Okay, and I think that is the last slide in the chapter. Now, this is a pretty hefty chapter, and I think you know my next statement. Nothing replaces reading the chapter. I can go over all this stuff in class. I can go through all the slides. There's still stuff in the book I don't have time to touch. Nothing replaces reading the book. Once you've read it, though, the summary, this is one of the longer summaries that I can recall in this book. Lots of italicized words here, all worth knowing. But it is still just a summary. The book will give a lot more detail than this. Summary of equations, 11, which is way more than normal too, but we've seen lots of examples here, and we've done done those examples. The key terms, the list is probably a little bit longer than average. Even though they give them alphabetically, they do list the page number where that term was first either introduced or defined or described. Then applying the concepts of multiple choice questions, probably a few more than normal, 51. Excellent thing to study for your test. They have the answers here. As far as I know, most of them are correct. And then they have questions for thought 12, that may be fewer than normal. But then for further analysis, 7, probably a few more than normal. So added together are about the same. Well worth thinking through those answers as well. The parallel exercises are a lot like those examples we did in the text. Those would be worth doing. For those one or two who had the big book, those have the answers in the back, but if you have the thin book, those answers were not included.
I looked at these questions for chapter 4. There wasn't many of them that covered on chapter 4.
What you mean? The multiple choice?
Concepts.
Uh-huh.
There wasn't many of them on chapter 4 test. Oh, you talking about?
Oh, wait, yeah. You'll not see any of them the same as the thing on the test, but the same concepts that are being reviewed there are basically what the concepts are on the test. They're definitely not going to be answered, the same questions with the same options. Definitely not. Okay. Now, for those with the big book, Chapter 7 is a chapter on light, which is a fascinating subject, tremendous subject. Wish we had time to do it, but we don't. Okay? In this, we have mirrors, we have, I know, the thin books, they cut it out because that's why they condensed the book, to save you money, because we didn't have time to cover them anyway. But if you have the big book, you'll see that lenses and mirrors, it's all really good stuff. I wish we had time. No, actually, you saved a lot of money by buying that one. You already got your money. Okay. In fact, the CD, compact disc, there's a lot of good stuff in there, and any of that would be a decent paper material as well. Just this can't be your source. This can give you ideas of it. So we're moving straight to chapter 8 then. Any questions on 6? Okay. Then we'll go to chapter 8. Okay, the test on Thursday will be on chapter 6. Okay? Again, let me go over it. We're going to do 2 hours and 45 minutes total of class here. We'll go into chapter 8 at 3:45. 2.5 hours. At 3:45, we'll stop chapter 8 and do the last lab for chapter 6. Then Thursday, we will continue in chapter 8 until either we finish it, and here's what I'm guessing. If we do finish chapter 8 on Thursday, what I may do is go on and give you the lab. If we get far enough in chapter 8 on Thursday, I'll go on and give you the lab so you can work on it at home if you want to, but if you have trouble with it or anything else, we'll be doing the lab in here on Tuesday. But it's just a take-home paper lab, nothing that you're going to actually be manipulating anything. We can't really manipulate very many protons and neutrons, things like that. So it'll be that kind of lab. So we'll see when Thursday gets here. Why was this not opening? There it goes. Just keep beeping at me. PowerPoint takes forever to load. What's that? I used to have a high-tech one up here. Oh, here it is. Oh, you have an old cheapie. Here's a high-tech one here. That's... Okay, finally this has come up. Okay, we'll do the slide from the current slide. And chapter 8 is the only chapter we have time to do in chemistry. It's supposed to be physics, chemistry. We've been mostly physics, a little bit of chemistry here. though we've had chemistry in the other parts too. But here we're talking about atoms and periodic properties. Okay? The core concept here in your text, for some reason they put white print on a yellow background, which is hard to read, but this is a little easier. Different fields of studies contributed to the development of the model of the atom. To me, that's a pretty lame core concept. This chapter covers a whole lot more than that, but that is a decent description. Okay, for sure they did. Okay? Atomic structure discovered, or at least theorized, or whatever, way back in the ancient Greeks. This is 460 to 362, somewhere in that time. I don't think he lived to be 98 years old. Maybe he did. But sometime in that time frame. Maybe. I don't know. It wasn't there today, so I don't know.
How old was Adam? Adam was pretty old.
Oh, yeah. No, way back then. Yeah. I can't think of the Methuselah, yeah, or something like that. He was the oldest. But anyway, Democritus, way back then, 4th century before Christ, way back then, he came up with the idea, and I think I've gone over this one before, that if you have a piece of material, whatever material it is, and you break it into smaller and smaller pieces, is there some place that you get down to you can't break it any farther and still have that same material? That's what Democritus' thought process was, and he called those tiniest little particles that can't be divided atoms. And actually, the Greek word for atom comes from the word indivisible. Okay?
You can split it out.
You can now. He didn't know that then. They didn't have nuclear weapons, or anything else. But his concept was, if you can take it as far as you can, and you can't get any smaller, that's an atom. And that actually was pretty good reasoning. Okay, they certainly couldn't do it, but they reasoned it. However, Plato and Aristotle came along about maybe a century later and said, no, matter is continuously and infinitely divisible. That is a continuum. There is no smallest piece. Okay, it's always, no matter how small you get it, will still be iron or copper or whatever it's going to be. So they sort of did away with Democritus' idea. He was already dead by then. Well, what was it? About 2,000 years later, not quite, yeah, more than that. 2,000 years later, John Dalton came along. I'm pretty sure he was British or Scottish. I think British.
While they was fighting, he was playing with Adam.
Yeah. Yeah, English chemist John Dalton, in the early 1800s, reintroduced this old idea about atoms, atomic theory, to explain chemical reactions. I don't want to get too deeply in this, but I will sort of give you a quick and dirty on it. Because of Aristotle, okay, remember he said there were only 4 elements. Earth, wind, fire, and water. Okay, those 4. Okay? And everything else is made up of those. And, thinking about it sort of, it seemed like that might be true or have some validity to it. But because he said it, everybody believed it. And so when the age of discovery was coming around, people said, hey, those are all really cheap things. Earth is there, free. Air is pretty much free. Water is pretty much free. And wind, air is, so let's, if everything's made up of this and we just need to combine those in different ways, we can come up and make gold out of really cheap materials, and platinum and copper and iron. Hey, let's get to going on it. So the alchemists, they call themselves, the chemist part sounds familiar, but the alchemists, they started the process of trying to get rich quick, okay, by doing this. So they started combining and heating and mixing and grinding and doing everything they could to try to develop, and sure enough, they found out they could combine certain things certain ways, and other ways they wouldn't combine, but and they started the process. But it was such a difficult process. They were very good at record keeping. So they recorded all their experiments and what they were going to try next and all this kind of stuff. And after a while, they had a pretty good body of information there. And as they studied them, John Dalton noticed that certain things only combine in certain ways. Like one oxygen would combine with two hydrogens. You never found just one hydrogen with one oxygen. It was always two. And carbon only combined one carbon with two oxygens. And one nitrogen with three hydrogens, and everything combined in certain.
How did they see atoms back
They
then?
didn't. Here's the thing. They noticed these ratios. On the macroscopic scale, they always followed these ratios. And therefore, they said there must be something on the microscopic scale that makes this happen. And that's where John Dalton reintroduced this concept of atoms. There has to be on the really, not just microscopic, submicroscopic scale, something has to be going on that they always react this way. So this is how John Dalton why he reintroduced that atomic theory that Democritus has just thought about, but he said we've got enough data to show it must be true. And not only that, that Aristotle was full of hot air. No, not mine. Okay, now this is a representation of an atom. A pretty poor representation. It's pretty, but the scale is way, 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 way off. What they've got, the purple and blue balls here, they represent neutrons and protons. I don't know which represents what. And then this cloud around here, there's a sort of goldy type cloud, and then outside of it is sort of a bluish type cloud. They're really not different colors, and neither are protons and neutrons, blue and purple. But this is just a representation, a model. Okay, and a really poor one, because the nucleus, which is the protons and neutrons, are so incredibly tiny. They're so packed together so tightly that you could hardly see them on this scale. Okay, they build them big so you can see them. The electrons, which by mass are probably even smaller than this than that, but there's not that many electrons. Those are just places electrons could be. They are incredibly small compared to the protons and neutrons in mass, but they take up huge volumes because they just bounce around all over the place. Not quite, sort of like that. And the reason they have two colors, there's inner shells and outer shells. Now, not just shells like this, there's some that are, globes or other things there. We're not going to get into that. But there's all sorts of structure in there that we don't, some people understand. But I don't totally, but I can sort of follow. Okay, so that's the model of Dalton's atom. Way too big of a nucleus, but really, 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 really massive nucleus. Huge electron cloud that has almost no mass at all. Okay, that's the structure. So here are the points of Dalton's atomic theory. That all matter is made up of indivisible atoms. Now, Dalton was before the nuclear age too, so he didn't know that it could be split. But all matter is made up of these units that cannot be broken down any smaller. Atoms. Indivisible atoms are almost redundant because atoms means indivisible. Now, an element, and we talked about this in an earlier chapter, I think it was chapter 4, is made up of identical atoms. So if you have a chunk of iron that's pure iron, every atom in there is an iron atom. Copper, same thing. Aluminum, same thing. Okay? If you have brass, not the same thing. You have some copper in there, and you have some other thing. Maybe iron, maybe zinc. Something else is in there. But things in, if you have oxygen, every atom in that is oxygen. carbon dioxide, some are carbon, some are oxygen. So an element is made up of identical atoms. Different elements have atoms with different masses. A really key thing that they didn't realize at the time, but they were beginning to realize that as time went on. Different elements have atoms with different masses. They knew that when they combined hydrogen with oxygen, it was always a mass of 2 to 16. Okay, I believe that's right, 2 to 16. Always in that ratio of masses. But later, when they split water into hydrogen and oxygen, you had twice the volume of hydrogen you did of oxygen. Okay? And they were going, wait, the masses are one way, but the volumes are a different way. And that's when they realized that different elements would have atoms with different masses. And an atom of hydrogen is so much lighter than an atom of oxygen or nitrogen or carbon or anything else. Chemical compounds, not elements, but compounds, are made of atoms with made of atoms in specific energy ratios, and that's what I was talking about before. Carbon dioxide is always 2 oxygens to 1 carbon. Always. Water is always 2 hydrogens to 1 oxygen. Always. And atoms are neither created nor destroyed in chemical reactions. You don't ever lose carbon when you're burning wood. The carbon goes from a complex carbohydrate, cellulose in the wood, to pure carbon, which would be your soot, that black stuff that gets all over everything, or to carbon dioxide, which is a colorless gas. But you never lose any. Atoms are never created nor destroyed in chemical reactions. They just react and are combined differently. So that was all part of Dalton's atomic theory. Now, on page 206, you'll see a subtopic here. And by the way, the big topic here is atomic structure rediscovered, okay, or discovered. And as Charles was saying, you can split atoms into smaller particles. I've already named them: protons, neutrons, electrons, okay? Well, J.J. Thomson in the late 1800s, probably shortly after Dalton's time, did that. He discovered the easiest ones to separate, those were electrons. And he performed these cathode ray experiments. Okay, now this will be sort of a picture of a cathode ray. What you have here is a very strong electric field here. You got a minus side here, a plus side here. And what you try to do is evacuate all the air out of that tube, okay? As much air as you can. Okay? Certainly you can't get it all, the pressure would be too great, it would collapse it. But you poke out all that you can, and put a very high voltage across that tube, and your cathode is here. Now, for some reason, I had in my mind that cathodes were the positive side and anodes the minus side. This has them backwards, so I must have had it wrong in my head. No, I know what I'm thinking. Cations are positive, anions are negative, but the nodes on the thing are reverse from that. So the cathode is where you have excess negative charge. Anode is where you have excess positive charge. So the charges, the electrons, flow in this direction. Okay? You certainly don't lose any material here or gain any material there except the charge. And those are the electrons. So that's his cathode ray tube experiments. He discovered these negatively charged particles. Now they were way too small to see, way too small to measure, but he could detect that they were there. Okay? Small, negatively charged, and someone named them electrons. And someone else, I think this may have been Ben Franklin, many years earlier, had, because he was late 1700s, he had named this, said, well, let's make the electrons negative. Okay, so that's what made them negative. He measured the electron's charge to mass ratio. He couldn't measure its mass, way too small. He couldn't measure its charge, way too small, but he could determine the charge to mass ratio of these things that he knew were moving from the cathode to the anode. He identified the electron as the fundamental particle. You cannot get any smaller than an electron, or at least we think. Now, if you read in the literature, they'll talk about electrons being made up of quarks, Q-U-A-R-K-S. Weird concept, and how they describe them are up quarks and down quarks, okay? An electron has so many ups and so many down, 2 to 1 or something like that. I don't even remember the ratio. It makes very little sense to me. I haven't done enough reading about it to fully understand it. But you can't break them apart. That's just what they're made of. That the electron is a fundamental particle. You can't get a charge smaller than the charge on an electron, and you can't get a particle smaller than the particle of an electron. Okay. Now, here's what he did. With this cathode ray tube, okay, he started firing the electrons off the cathode, the negative charge plate, through an open positively charged plate, and he did what they call a collimator, plates here that had a charge on them, positive and negative on one side or the other. And what would happen, he would bend this, the stream of electrons that were coming through here, a very narrow band, that's what made it into a column, but he also put it inside a big, strong, permanent magnet, just like we talked about before in some of our other devices. So you had deflection going on of the charged particles between the plates. You had deflection going on with the magnetic field, and then you had a detecting stream here that the deflection depended on the charge to mass ratio. By different amounts of charge across the plates or different strengths of the magnet, I imagine he kept that pretty constant, he was able to determine the charge to mass ratio. Now this is just a quick and dirty on it. It's a lot more complicated to actually figure out all those angles and that kind of stuff too. But those deflection angles depended on the charge to mass ratio. Part of what was going on there, he was trying to have everything with equal momentum, but if the mass was greater, then the momentum was greater, velocity, all those things were coming into play here. Positive and negative charges deflected in opposite directions. If there were both charges coming through here, some deflected one way, some another way. That was mostly from the magnetic field, but also from the electric field. So it was a pretty complicated experiment, just especially from back in those days. And it did show him that there were these particles out there. The best he could do was determine a charge to mass ratio. Now that's J.J. Thomson. Don't confuse him with William Thomson, who lived many years before. He was the one who came up with the 3 laws of thermodynamics. We talked about him in chapter 4. He was also Lord Kelvin, by the way, that they named the Kelvin scale for. This is J.J. Thomson, spelled the same way. Now, not spelled the same way as Benjamin Thompson. Remember, he's the one who was the British sympathizer during the Revolutionary War. He went back to Britain. They made him a count to reward him for coming over. He was quite a good engineer, and he's the one that discovered that energy was not a material, but actually was a form, that heat was not a material, but a form of energy. Okay, lots of similar names. J.J. Thomson. So, he could give you a charge to mass ratio. Along came this other guy named Robert Millikan, about 1906. So we're getting up into the last century now. Okay, 1906, Robert Millikan. He studied, it's a really nifty experiment. Let's see if I can show it. Kind of. Okay. What he did, you've seen these little aerosolizers. You squeeze a button, forces air over the top of a fluid and picks up just a few droplets and sprays them. You know, the wife puts perfume on that way, that kind of stuff. So he has these little bitty droplets of oil, okay? Sprays them over this. Now, gravity is going to tend to bring those down. But you see, most of them played out on top of this, but a few of them make it through the hole in the center. So you have a very small, thin column of droplets coming down. But he has a very strong electric field here. Positive charge plate up here, negative plate down here. Gravity is trying to pull these droplets down, right? The weight of them coming down. However, your electrostatic force, because they're coming through the positive plates here, they become positively charged, and there has to be an electron source here, and the electron source, because they're slightly negatively charged, they tend to go toward the positive plate and away from the negative plate. So you have gravitational forces pulling down, electrostatic forces going upward. And what you do, you have a viewing scope over on the side, and you do your light in a certain way that you study the droplets. And the lenses inside the viewing scope have these little lines on them. And they represent, they're very carefully calibrated, how far the droplets are falling. So you can measure how many millimeters they drop. And you can time it. So you see a drop come in, and you time it, and you time its fall. And sometimes while you're timing it, it stops and starts moving up. It's picked up an electron and now is moving back up again. So you look at enough of these and time enough of them. Those that fall straight down the fastest, they're moving by gravity alone. Okay, and you generally have a pretty good idea what the size of these are, what the mass of them are. So you get an idea what the force due to gravity is. Any that are moving slower have some fixed charge on them. Remember, your charges can only be by integral numbers of electrons. So some of these that go down more slowly, they must have 1 or 2 electrons attached to them. Those that stop, they have a certain number. Those that start moving back up have a certain more. So you measure as many of these as you can, and you'll find they all fall into certain categories, okay, depending on how many electrons they picked up. The charge on the droplets are multiples of electron charge. So when you get the charge from here, you can tell what the charge on an electron is going to the least common denominator. You know, what's the smallest charge you can have? And then Thompson's, which gave you mass to charge ratio. And if you know the charge, then you can get the electron mass. You'll never measure the electron mass, but you can measure, as Thompson did, the charge to mass ratio, combine that with Millikan's charge, and you can calculate the mass. Okay? Sort of like that experiment we did with the pendulum. Okay? You can measure the height here and figure the gravitational potential energy. You know that's how much kinetic energy you have at the bottom, and even though you don't have a device to measure the speed there, you can go back and calculate the speed. Same thing here. You can measure the charge to mass ratio from Thompson's result. You can measure the charge from Millikan's result. That gives you, by calculation, the mass. Pretty clever, and actually I got to do this experiment the first quarter I went back to grad school. I was trying to find 4 courses to take so I could have a full load so I could get the GI Bill. And one of those courses happened to be a physics lab, and we did Millikan's oil drop experiment. It was tedious, but it was really interesting. Okay. So here is Thompson's result, that the charge to mass ratio, I doubt if he had this many significant digits, but let's say pretend he did, was 1.7 times 1.7584 times 10 to the 11th. So that's a huge number of coulombs per kilogram. But a kilogram is a huge amount of mass. So he didn't probably use that. He probably used coulombs per gram or something even smaller. Millikan's result was that the Q, the charge, was 1.60. I doubt if Millikan quite got that precise, but maybe he did, times 10 to the minus 19 coulombs for every electron charge. That was the Q. So if you put this Q in for there, and then solve for mass, you then have multiply both sides by mass divided by 1.7, blah, 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 and you get 9.11 times 10 to the negative 31 kilograms. Now, why would you use kilograms, which is such a large unit? It's a SI unit, that's why. But I would have used grams or milligrams or micrograms or something to get that number to be a smaller exponent. But anyway, that's what you get. So this is how they were able to determine, not by measuring, but by calculation, what the electron mass was. And it is tiny, 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 tiny. One of the smallest particles you'll ever calculate. Okay. All right. So let's go back and look at some of these early models of the atom. Not way back to democracy, starting with Dalton. Dalton said atoms are indivisible. Smallest particle of a certain material that you can get. Okay? Thomson and Millikan, they combined theirs together and found out the electron mass was extraordinarily small, and they couldn't measure a volume. It was just beyond them to measure the volume. In fact, I'm not sure anyone can measure the volume of an electron. So what is the nature of the atom's positive charge? Well, Thomson, J.J. Thomson, same one, had this model, and it's sort of like the picture we saw earlier. He called it the plum pudding model. He thought the atom was there, and it's made up mostly of protons and neutrons with electrons stuck in like raisins in the plum pudding. Okay? Why would you call it raisin pudding? I don't know, but anyway, it's a very British thing. And the electrons were embedded there in a blob of positively charged matter like raisins in a plum pudding. Okay? I like the sound of that because I love to eat, but that's not, it turned out not being the case. And here's how we found out. We began to learn more about the nucleus by a scientist called Ernest Rutherford. Now, from the more I've read about Ernest Rutherford, he must have been a character. You picture these scientists as being very serious and single-minded and, very bright and very dull people. I don't think Rutherford was, okay, anything close to that. And this is followed shortly after Millikan's oil drop experiment. He used y'all know what aluminum foil is, right? It's basically pure aluminum, but it's been heated and run through rollers until it's so thin, can't see through it, but it's really, really thin, okay? Well, he did the same thing with gold. Maybe back when gold was cheaper, but very small quantities of it. Roll it, you heat it, roll it until it's very thin, almost thin enough for you to see through. Probably not quite. Very, very cold, thin gold foil. Gold, like aluminum and copper, are very malleable. You can make very, very thin sheets of it. So he started that, and he scattered these alpha particles, which is a form of radiation. It's actually the nucleus of a helium atom is what it is. 2 protons and 2 neutrons. But you can get sources for these alpha particles and fire them through them. Because they're positively charged, you can accelerate them and fire them through a gold foil. Now, if Thomson's plum pudding model was correct, gold is pretty densely packed, and therefore very few of those alpha particles should get through because they should bang into the gold foil and be stopped. But the surprising thing was most of them passed right through with no significant deflection. Wait a minute, okay? You didn't have a single layer of gold. You had probably several molecular layers of gold, and still these fairly massive alpha particles, 2 protons, 2 neutrons, went through it. with no deflection. Now, a few were scattered at really large angles. So most went straight through, others were deflected back big time. What in the world is going on here? Here's maybe a picture of this. Yeah. Here's his gold foil here. Very, very thin sheet of gold. Here's his radioactive alpha source, and there's several different things you can use. He identified one of them. And these were collimated, so they were coming through in one direction, and he was expecting hardly anything to get here. Most of them get bounced off somewhere else, right? What happened? Most of them came straight through with no deflection at all, and a few of them were bounced at really big angles, okay? Really big angles, way back here and here, but most of them came straight through. Just amazed at how many. So what's his conclusion? The atom's positive charge that would be attracting these alpha particles, I'm sorry, not attracting, repelling these alpha particles, those alpha particles are plus 2 charges, they should have been being bounced backwards by these nuclei. They were extraordinarily small and very extraordinarily massive nuclei. The positive charge resided in a very small but hugely massive nucleus. Okay? And then the rest of it was empty space with a few electrons flying around. So that's why very few of these were deflected, and some of them at very large angles. Those were the ones that did hit that nucleus and get reflected backward. But most of them went right through that electron cloud because there was no nucleus in the way. So this was later someone identified the positive charges in the nucleus as being protons. Okay? And James Chadwick, which is much later, 25 years later, also determined that there were some neutral neutrons in that nucleus. You couldn't identify them by charge, but the mass was just too much to be just protons. And he found out these neutral neutrons. So lots of names here, which means lots of potential paper topics too, you know. How have we hit today? J.J. Thomson, well, we did Democritus, Aristotle, Plato, Dalton, J.J. Thomson, Rutherford, Millikan, I mean, Chadwick, just tons of them here, okay? But he discovered that there were also neutrons in that nucleus. So here's the general idea. These positively charged alpha particles, 2 protons, 2 neutrons. Now they probably didn't know they were neutrons yet, but they knew they were positively charged protons. They went through, now this is showing the gold foil to be 3 atoms thick. And most of them went right through because they would pass through the electron clouds. The very few ones that happened to hit that nucleus in the middle, they were deflected back pretty sharply. Most of them went through with no deflection at all. Others may have hit just the edge of that nucleus and deflected at smaller angles, but most of them passed right through with absolutely no interference with that. So you knew the plum pudding didn't work, okay? It wasn't a massive pudding, it was just a few electrons scattered around. You had a very tiny, tiny volume of mass, but very, very massive in the center, and then this cloud of electrons floating around that took up absolutely almost no mass at all, took up a huge amount of volume. As my brother's physics teacher said, most of everything is nothing. Okay, strange, but true. All right, so let's look at the nuclear atom. Now, before we go back, or proceed, top of page 208, the discovery of the electron. They name a new person here, William Crookes. His Crookes tube, I think was what these cathode ray tubes were, originally called Crookes tubes. Michael Faraday came up with the name cathodes and anodes and things like this. There's another name, okay? and J.J. Thomson used these, and a pretty good little case study there, well worth a read. And then on the opposite page, page 209, is a description then of Milligan's oil drop experiment. Okay? Now this is talking as if it's more Thomson, but actually this should have been Milligan. I don't know why they mentioned Thomson. Okay. Now, let's look at what we call the nuclear atom, which is rather strange. It's talking about the atom, which has a nucleus in it. Okay? There's several numbers associated with every atom. The first of these is the atomic number. Okay? The atomic number is how many protons are in that nucleus. Okay? If there's only one proton in a nucleus, you're guaranteed that's a nucleus of a hydrogen atom. Guaranteed. If there's two protons there, it's lithium, I believe. Gotta go back and check my table. No, I'm sorry, helium. Of course I knew helium. 3 would be lithium, 4 would be beryllium, 5 would be... So every element has a unique number of protons. If it has that many protons, it's got to be that element. No way around it. The atomic number absolutely identifies what element you're talking about. No questions asked. There's no integrate between them. If it's got a certain number, give me a number. Make up a number, anywhere between 1 and 100. 70. Okay? Go to your periodic table and look up everything that has 70 protons in it is, you would have to get one that's hard to pronounce, ytterbium. Okay? Its symbol is YB. Okay? That's number 70. It's a rare earth, very rare. Never run into it and probably ever tried to pronounce it before in my life. Thank you very much. Okay. But everything with 70 protons, and only 70 protons, has to be YB, ytterbium. Okay? Same thing. Pick a number, something basically between 1 and 100. Every number represents a different element. Elements are distinguished by that atomic number. Now they say here, this slide is sort of old, 113 elements have been identified. If you look at the periodic table in the back of my book, it actually indicates it goes up to 118. However, some of these I think are theoretical and actually may not have been identified. Those that start with UU, I think they have a concept that they're out there, but no one's ever identified them. Okay? And in this table, I only see 2 of those, so that would get you up to 116. No, I see 3 up. 3 up. No, 4 of them. So 4 from 118 would be 114. So there must have been one more, or either I missed one. Okay. 113 is a UUT, 115 is a UUP, 117 is a UUS, and 118 is a UUO. Those are the only UUs I see here. What's that? Which number is that? 110. No, actually this one that's called DS in this one. So evidently they have identified one more since that one. Yeah. See, mine may be a newer edition than yours. Let me find it in chapter 8 and see if it's the same. Oh, I'm in chapter 8. Duh. 217 or somewhere thereabout. Not my 217. It's my 218. 210. There it is. It's 220 in mine. 110 here is DS. So they must have discovered one since then. So that must be the one that we're, because My 109 is MT, 110 is DS, 111 is RG, 112 is CN, and 113 is UUT.
So 111 is RG.
Yeah, that's what they got in mine. What do you have in yours?
UUU.
Oh, see? There must be more of it. So this book, it must be an update from that one. So they have found a few more. This says 113. I think my book says 114. They are occasionally finding a few more. Now, every now and then they'll find out something they thought they had really wasn't. So they'll go back and take them out. But I think we're up to maybe 114 or maybe even higher now.
How would they find this on other planets or something?
No, what they are, they're very short-lived things resulting from atomic reactions. They bounce things off like the colliders. They bounce things together, and then they'll find a trace of something that happens for just a millisecond or so and then disappears. It breaks down to something else. If they find it for long enough and identify it, they can give it a name. But they're very short-lived. Everything, you see the parentheses there around the atomic masses? That means they're radioactive, and they don't know exactly. That's just an average mass. And almost the last row and a half, and then a bunch of those at the bottom, they have parentheses around them there. They're not stable. Now, if you talked about stable elements, there's far fewer than this, fewer than 90 probably. Okay. But the number of protons that are in the nucleus, that does not change. That makes it whatever element it is, and it's there. Usually that equals the number of electrons that are flying around it, at least if these are neutral atoms. And when they say neutral atoms, they mean electrically neutral atoms. The atoms that are flying around in that tube up there, producing the light, those are ions. They are not atoms because they have some net charge, either excess electrons or deficit of electrons. So, but the number of protons always stays the same. So, if the number of protons stay the same, does that mean all nuclei of that material, like iron or carbon or whatever, is always the same? No. Number of protons may be the same, but you may have different numbers of neutrons. Okay? Now, let's take the simplest one. What's the smallest atom out there? Hydrogen. 1 proton is all it's got in its nucleus. Except, maybe 1 every 10,000 or so, you'll have 1 neutron in there too. Okay? And maybe 1 out of every 10 or 15 million, you'll have a second neutron. Okay?
Why wouldn't it be something else?
Well, it's always hydrogen because it has 1 proton. All 3 of those have 1. So if you have different number of neutrons, then you have different isotopes. It's still hydrogen, but one of them is 1 mass of hydrogen, one's a double mass of hydrogen, one's a triple mass. Still a single hydrogen. And hydrogen shows up worse than anything else because it only has 1 proton. Okay. And this is how we talk about it. That hydrogen 1 is our normal hydrogen. 1 proton with no neutrons. So therefore, we put the mass number on top, which is exactly opposite of how our book does it. The mass number on top and the atomic number on the bottom. Atomic number is how many what? Atomic number is protons. How many protons? And generally, for neutral atoms, that's how many electrons as well. The top number is the total protons plus neutrons, so this one has 0 neutrons. This is the atomic mass of that hydrogen. This one, however, has 1 proton, making it hydrogen, but it has atomic mass 2, which means it has a neutron. And because it's twice as massive as normal hydrogen, I mean, that's twice as massive, it's called deuterium. 2 times the mass, duo 2, deuterium. Hydrogen 3, on the other hand, is still 1 proton, making it hydrogen, 3 atomic mass units. That means it has 2 neutrons. three times the mass of a normal hydrogen atom. Now, there is a very good use for this deuterium and tritium. Okay? Any water that has in it, remember water is H2O, 2 hydrogens, 1 oxygen. Most of the hydrogens out there are single hydrogens, like that, hydrogen 1. Okay? However, like I said, maybe once every 10,000 atoms, you'll run across a deuterium. When you find that, then that water molecule, if it happens to be in a water molecule, is a little more massive than most water molecules because it has an extra neutron in it. And that's called heavy water. It's not noticeably heavier, but it is heavier. Because of that extra neutron, that is going to slow down radiation. That's why, one reason, every nuclear power plant that you'll ever see, I think, is always on a river or a lake or the ocean, okay? Because they have a ready source of water and they're always trying to extract any deuterium or tritium, heavy water that they can, because that heavy water blocks radiation far better than normal water does. That extra neutron really inhibits radiation movement. So this is your convention. You write 2 numbers to the left of your symbol, your periodic table symbol, elemental symbol. The lower number is the atomic number, the upper number is the atomic mass. The upper number is always greater than or equal to the lower number. Okay. So there's hydrogen. Okay? Now, the atomic symbols and the numbers, that's what we've been talking about, and the masses. The mass number, as we indicated, number of protons plus number of neutrons. Notice what are they not even counting? Electrons, because those have such tiny masses, they don't even tip the scale, okay? They're about 1/10,000th the mass of either a proton or a neutron. So if you wrote down 1 to get the electron, you'd have to 1.000. Okay? You'd have so many decimal points out there with zeros in between, you don't even count. Okay. Now, when I was growing up, an atomic mass unit was called an AMU, atomic mass unit. Now they just call it units, okay? To me, there's something missing there. It should be AMU, but they call them U, okay? And what an atomic mass unit is defined to be 1/12 of a carbon-12 isotope mass, okay? Well, carbon-12 is the most common isotope of carbon. It has 6 protons, 6 neutrons, for a total atomic mass of 12. And 1/12 of that is 1 AMU. It seems crazy to me. Why wouldn't they just say a hydrogen proton is 1 AMU, 1 U? But no, they do 1/12 of a carbon-12. Okay, fine. Go for it. See, hydrogen is so much harder to isolate than carbon is. So what's the atomic weight? The atomic weight is the atomic mass of an element. So when you see atomic weight, atomic mass, that means the same thing. They're not making a distinction between mass and weight. Average over the naturally occurring isotopes. Okay? Now that's sort of a vague sentence, but if you, or phrase there, but if you think about it, it kind of makes sense. Here is the example back with hydrogen again. Now this is exactly the same thing we showed before, so there's nothing new here. But let's say 98% of the hydrogen was this, okay? And 1.7% was this, and 0.3% was that. I'm just making up those numbers, they're not what it is. So what would be the atomic weight? You would average all those together by percentages, and it would be very close to 1, but just a little bit more than 1 because these bump it up ever so slightly. And if you'll look at the periodic table in the back of your book or in chapter 8 or wherever you find it, and look at those atomic masses, hydrogen is 1.008. So it's not just that one proton. About 8 times every 1,000, you'll find at least a deuterium somewhere around. Okay? Boron, helium is 4.003. Maybe 3 times every 1,000, you'll have another extra proton, neutron. Most of them have 2 neutrons, but maybe one every 10,000 or 1,000 or something like that will be an extra, a third neutron. And you go on down the list like that. Lithium, most lithium have 4 neutrons, but not all of them. Some of them only have 3. So not always is the isotopes extra like neutrons. Sometimes there are a few less. So lithium is mostly 4 neutrons, but occasionally has a 3. Beryllium's usually 5, but sometimes 6. Boron is usually 6, but sometimes 6, but sometimes only 5. Carbon most of the time is 6 neutrons, but occasionally there'll be a 7th. 6 protons, 6 neutrons. So you go down the list like that. The difference between the atomic number mass and the atomic number is approximately the number of neutrons, and when it comes up being decimal, that means you have some isotopes with extra, or some isotopes, if it's a smaller number, with fewer. So an atomic mass of an element is averaged over the naturally occurring isotopes. Let's see if we can find another example. Okay, here's nitrogen. If you look in the periodic table, nitrogen is number 7, but its atomic mass is 14. So that means most nitrogen have 14 neutrons. All nitrogen have 7 protons. That's why I said it wrong. Most nitrogens also have 7 neutrons, except occasionally you'll have a nitrogen with 8, which would be N15. So here's your N14, 7 protons, total protons and neutrons of 14, meaning 7 neutrons. Most of the time. This is 99.63% of nitrogen is N14. Okay? 99.63%. That means 0.9963. Okay? So fewer than 4 parts of 1,000 out of 1,000 are going to be N14. Okay? So what you do, you take this mass, 14, multiply it by 0.99, or 0.9963, okay? And then for N15, which has that 8th neutron, okay? That's a frequency of 0.37% or 0.0037. Multiply that by the atomic mass of that N13, so that would be this one. The percentage here times this atomic mass, which is 14.00. Add those together. This number is going to be very close to 14, a little bit less. This one will be a little bit more than 14. Add them together and you get 14.0067 atomic mass units, or U. Okay. So that's the number I think you see in the back of your book. If you look for nitrogen, number 7, they say 14.01. And you see the 6 rounded the second 0 to a 1. Okay. So that's why the atomic masses, whereas the atomic numbers are always integers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 116 or whatever it is. The atomic masses, however, are not. On the symbol here, they round to the nearest unit, but the actual number of the atomic mass is actually, for nitrogen, is 14.0067, which is in my book rounded to 14.01. Okay. That's taking into account a few of these, not many, a few of these 15s, and most of them are less than that. All right. Any question on atomic symbols and masses? Okay. Now, there are a lot of blurbs in this chapter. The case study at the top of 210 or somewhere thereabout is the discovery of the nucleus. You start with J.J. Thomson's discovery of the electron and his theoretical idea of a plum pudding. You keep studying and you reading there, you see Ernest Rutherford is the one that his discovery basically wiped out the possibility for the. In my book, it's 210. It's called Discovery of the Nucleus, case study. It's a sort of a, I don't know, brick kind of color, kind of not quite pinkish, but close to it. It may not be in the old book. And this is basically Ernest Rutherford. Another example of a good possible source of information, but can't be a source of your paper. Now, I'm trying to find this classic atom. It's somewhere around that page. That's why I turned to it. They just don't have this subtopic in the newer text, which is in the older text. Your classical atoms. Predictions of the classical theory that electrons flew around the nuclei. Yeah, that makes sense. A lot like the planets going around the sun, right? Now, here's where classical theory kind of falls apart. Because the electrons are moving in a curved path around the nucleus, they must be accelerated. Centrifugal force, bringing them in. Okay, now, if you follow this logic, accelerated charges radiate. We've already talked about that, right? A moving charge emits a field, magnetic field, electric field, whatever. They radiate, okay? If anything that's radiating is losing energy. So if this thing was actually radiating, then the electrons would be losing energy, and ultimately they'd spiral into the surface. And if that happened, then the electrons would be in the nucleus, atoms wouldn't exist. Obviously not a right model, okay? We know that atoms do exist. So a new concept, a new theory was needed. Now, from what I understand, I read this or heard it somewhere many, many years ago. It was right around 1900. Physicists said, we got Newton, we've got Lord Kelvin, William Thomson, we got just about everything we need. Our job's almost done. These other scientists, they still are building their fields. We've got it all figured out. We've got motion figured out. We got energy figured out. We got momentum figured out. We got all this stuff done. There's really not that much more to study. There's just a few little nagging issues here and there. Once we get these done, probably within a lifetime or two, 1 or 2 generations, we're going to have the whole field of physics thoroughly understood. And then man can go on from there. Until someone came up with this idea. This is one of those loose threads. We got to figure out what to do about this. If we can get this knocked, we can tie it up and go home and have a vacation, okay? Because we got it pretty much done. This new theory is needed. Well, this new theory turned out being quantum mechanics. And the more they found out about quantum mechanics, the more they realized we didn't know beans, okay? The more we discovered, the more we learned we had to discover. And maybe before I go here, I just noticed this table 8.1. I don't know if this is in your book. In my book, it's a green table, dark green table number, and then lighter green Yeah, you got it. Here are your stable isotopes. You got regular hydrogen and deuterium. Now, I think tritium is stable too, but it's so small of amount they didn't even list it. So they list the mass of the isotope that is pure hydrogen, okay, and its abundance, which is 99.9185%. That's 0.00015. I'm sorry, 0.9998785. So it's very, very prevalent. The deuterium is only 2 every 10,000 or 100,000 or something like that. So you multiply the mass of the isotope times the relative abundance as a percent and add those totals together and you get 1.0079. Okay, not far off from what regular hydrogen was, which was 1.007, but a little bit higher because the other isotope was larger. Beryllium, the major one, is here, and that's just about all, babes. That's all they got, 100%. Nitrogen, a little bit, mostly 14, very rare that you get 15, but occasionally. Oxygen has 3 stable isotopes. O16, which is the one we're probably most used to. Eyes nuts on me. It's almost like, I hope it's not going to be, but it's almost like a migraine's coming, but I hope it's not. Then you have also O17, which is 16.999, and O18, which is 17.000. Now, I think they got that wrong. That's got to be 18.000. Can't be 17. On oxygen. The third one there, 18.8. That's 18 atomic mass, 8 atomic number. Oxygen, it doesn't go from 16.9914 to 17. It goes to 18.0. Okay, it's got to be. Yeah, I know, and I don't believe that could possibly be true because that's not 18, that's closer to 17. So I think that has to be an 18 there, 18.00016. Okay, fluorine is 19, 100% of that, at least in what we know already. Neon, notice, has 3. And aluminum, only 1 isotope, stable isotope. Okay. There's another concept applied here that's on atomic parts, and basically your lab is going to be doing something very similar to that. The first part of your lab is going to be doing something very similar to that little block up there. So here's the quantum concept. In my book, it's called the Bohr model, and under that, quantum concept. Now, we're not quite to Bohr yet. Before Bohr, we have Max Planck, a German physicist who did some of the very early work on quantum mechanics. He introduced this idea of quantized energy, that everything gives off little quanta of energy, little packets of energy, all pretty monochromatic or monoenergetic, that you don't have just a distribution of energy, a continuum of energy, you have these quantized little packets. Now, Max Planck, one of the greatest German scientists, they had a bunch of them, but he's one of the greatest, and throughout Europe, mostly Germany, and a lot in Germany, are these Max Planck Institutes. Okay? where you can go and study, and you can study all sorts of things there. It doesn't have to be science, but they like big universities, okay? We have friends here in Birmingham, who, the guy is from Munich. That's where his parents lived. That's, I guess, where he was born. And he grew up in that area. He's a scientist at UAB. Pretty bright guy, too. Very bright guy. His father was an engineer at the Max Planck Institute just north of where they lived. Okay? I can't remember the name. Galmush or something like that. The town north of Munich, the suburb north of Munich where they live, and just north, the next train stop north of them is Max Planck Institute. So when we went over to visit Olaf's parents, and they treated us, they were such nice people, and took us around, showed us Munich, drove us around Germany. I mean, they were just great people. But he took us and gave us a quick tour of Max Planck Institute. He had already retired, so he couldn't get into all the places, but he showed us around the campus. Really pretty fascinating place. We also have some very good Italian friends who now live back in Italy. They're not here anymore. But they had a son who was born here in the U.S. After Fabio finished his PhD, he was a classmate of my wife's. And after he graduated, he moved to Boston with a job for a pharmaceutical company, and that's where his son was born, Giacomo. So Giacomo was then an American citizen, also an Italian citizen, but an American citizen. Giacomo and Fabio, very bright, really brilliant, and Giacomo's a really sharp kid too. Well, when Giacomo was getting into junior high and high school, actually they came back for 1 year. I think Giacomo was maybe in 6th grade or something. And we met the two sisters too, but they were born back in Italy. But anyway, we went to see them in Italy one time, and Giacomo was like a sophomore or junior in high school by then. Really bright kid, really bright. He could go anywhere he wanted to, really bright. So his parents wanted him to have the opportunity of either going to university in Italy or coming to the U.S. Since he was a citizen of both countries, he should be able to choose. And they favored the U.S. because Italy's education system is great, but it just doesn't have all the opportunities ours does. So we got to know him, and he entertained us a lot there, taught us card games, and he was just a good kid to be around, and a high school kid, and just, it was a lot of fun. And they saw how well we got along with him, because Fabio was at work, Rita had things to do, and he did. So they got to talking about it the next year. They'd love for him to come to the U.S. and do his senior year of high school here in the U.S. to improve his chances of getting into U.S. university. They were afraid if he just did his high school in Italy, they may not have a good chance. So they started looking around. They had lived in, Birmingham before, and they found this one private school that would take him, no questions asked, and and it was right up the road from where we lived. And they asked us if we would consider hosting him for his senior year of high school. We said, sure. We had such a good time with him. So we had a senior foreign international kid come in to live with us, and he was fun. He was a little bit of a pain too, but he was fun, And we had a good time with him that year, and he graduated from the school, did quite well, even though the school officials thought he would need to be in a slower class or something. They said, no. My wife was very adamant, no, put him in these classes, and he aced them. He did quite well. It was hard because English wasn't his first language. Italian was, but it was Altamont. It's a small private high school there on top of Red Mountain. But it was a pretty good school. So anyway, he graduated from here and went back to Italy. Well, in Italy, they have 5 years of high school, so he did his 5th year back there and graduated from there as well. And then he came back during that 5th year to check out some schools in the U.S., and he got accepted at several. He relied on us to help him with the application processes because we're used to them. And he got a full ride scholarship at University of North Carolina, Chapel Hill. Go for it, you know, great school, paying everything, that'll be fantastic. Well, he was considering it. Got rejected by a few, accepted by several, but then he got accepted at Harvard. And his mom loved Harvard. She loved Boston. That's where he was born. He just felt he had to go to Harvard. Well, they weren't giving him a full ride scholarship like UNC was, so his family basically sold their house and moved to an apartment so they could afford for him to go to Harvard. And but anyway, what's that? Well, he put them through it. He wanted, they got willing to do it. We told him what well, we didn't quite say that. Our German friend told him what an idiot he was for passing down a full ride at UNC, but he wouldn't hear of it. So he graduated from physics at Harvard. Then he went back to,
I didn't think Harvard was known for it.
it's not. It's known for its name. It's got a good physics program, but MIT would have been far better, and that's right, you know, next door to Harvard. But he didn't like MIT's campus. The buildings didn't look as pretty. Dumb kid, you know. But anyway, he graduated from there. He's now working on a PhD in Europe. He did his research at Grenoble, France, and now he's back at school at Max Planck Institute in Munich, where Olaf's father worked, that we visited the campus. So small world. Sorry I got off onto that. Max Planck came up with this idea that the energy...
You really don't like that.
What's that?
You really don't like being there.
Actually, he didn't at first because he didn't plan for a place to live, and Munich is hard to get housing in New York City. So he didn't like it at first, but I think he likes it far better now. We got to talk with him sometime. So anyway, Max Planck came up with this idea of quantized energy packets. And here's how he said it. That energy is not a continuum, but is discrete values, and this was his formula. E is equal to h times the frequency. Now the frequency is the photon frequency. H is a constant. That's your constant of proportionality. Energy is proportional to frequency. We know that. Light energy, infrared energy is lower energy than ultraviolet energy. Ultraviolet energy gives you skin cancer. Infrared energy just heats you up. You know, there's no damage there. And there's a very small difference in those frequencies. So the higher frequency, the higher the energy. The lower frequency, a little bit less energy. And it goes by these packets. And a certain frequency will always produce a certain amount of energy. That's why gamma radiation is so bad, because it's very high frequency, high energy radiation. Okay? And this is Planck's constant. And it's a very small number. 6.63 times 10 to the negative 34 joule seconds. Okay? Now, joule second, why is that? Well, this energy is in joules. Frequency is in per second. So this would have to be joule second. So the second cancels out the per second, and you get joules. So there's what we've got. Planck's constant named after Max Planck. Okay? Pretty nice formula. Nice one to remember. Then, about 5 years later, this strange fellow named Einstein came along. And not only did he build on Planck's idea of quantized energy, he said light itself was made up of these quantized photons. I just mentioned different colors of light have different energies. They're very similar, very close, but not quite the same. The higher energy protons have more energetic photons. That's why the energy of the light coming in the window of your car out there is the basic spectrum of white light. It comes in, but in going through the glass, it loses a little bit of energy, so it drops down a level, and some of that energy that was the light drops the infrared energy, which becomes heat. And that's why the cab of your truck or car heats up so fast, up so much in the sunlight like this, because it's lost energy coming in through the glass, and it can't make its way back out again because it doesn't have enough energy to go through. So the higher energy photons are the more energetic photons. Now, before we move on, I think we'll use this space here. We have reached example 8.1. What is the energy? So we're looking for E. Oops, I got to get my pen recolored. Okay. We're looking for E. What is the energy of a photon of red light? And red light has a frequency. Frequency is F. I'll put F for R for red. Of 4.8. I'm sorry, I can't read. 4.60 times 10 to the 14th hertz. Now, what is a hertz? A hertz is a per second, okay? Cycles per second, cycle per second, okay? So that's the frequency of red light, 4.6 times 10 to the 14th hertz. Well, from what we just saw, Planck's constant, and there is Terry. Okay. Yep. That's all we got today. Planck's constant is 6.63 times 10 to the minus 34 joule second. So Planck's constant H is, I'm not going to turn back there again, 6.63 times 10 to the minus 34 joule second. Okay? And what was Planck's law? E is equal to what? HF. And here we got it. H is 6.63 times 10 to the negative 34 joule seconds multiplied by F for red, so this is the energy of red light, would be 4.60 times 10 to the 14th. And a hertz is a per second, 1 over second. Okay? So obviously the seconds go out, and that leaves us with joules, which is what we got, but it's a very small number. The energy of a photon of red light would be, if someone's got a calculator, you'll need to use your scientific notation mode, 6.63, and then usually you use the EE or EXP key to represent the scientific notation. So if you press that key and then press the minus key that comes with the, I'll sort of show you, you would enter 6.63, then press either the EE key on some calculator or EXP on some calculators. One of those two keys, and then press the negation key. That's the minus sign that's in the parentheses, not the subtraction minus key, the one in parentheses, and then 3/4. Yeah. What do you get? 3.05 10 to the minus 19 joules. Got it. And I don't know a prefix small enough to get you that to a bigger number, but that will do. 3.05 times 10 to the minus 19 joule. Exactly. Okay? Now, if any of you need help with the calculator and the exponential notation, I'll be glad to help that. What's that? 3.05 times 10 to the minus 19. Did you get that? Okay, good deal. Okay, example 8.2, what is the energy of a photon of violet light? So this will be E sub V. If violet light has a frequency, so F sub V, I was starting to give you a wavelength, F sub V for violet light, not far off, but a little bit, 7.30 times 10 to the 14th hertz. Remember, hertz is a per second. So basically we do the same thing. We do Planck's constant, 6.63 times 10 to the minus 34 joule second times 7.30 times 10 to the 14th per second. That's what a hertz is. The second and the per second cancel out, and what do you get there? 4 point? Yep. Anybody get it? 6.63 times 10 to the minus 34 times 7.30 times 10 to the 14th. 4.84 times 10 to the, again, negative 19 joules. So it's not a lot of energy difference, but it is some energy difference. And guess what? Red is down near infrared heat energy. Violet is up near ultraviolet, the frequency that damages. You know, it causes skin cancer, cataracts, wrinkles. It basically is what ages you, is ultraviolet light. Okay? Now, let's clear that out of the way because I know we're going to have another slide coming up here. So let's look at the atomic spectra. Okay? Now, everything emits energy. I mean, you are emitting energy right now. Your heat that's being put up, it's leaving your body. Okay? If someone were to put a sensitive scope on you, like an infrared scope, they could tell there you are. Okay? A lot of this that is being put out is called continuous radiation distribution. That's black body radiation. Just an object there emitting a whole bunch of different energy. Continuous radiation distribution. It depends on the temperature of the radiating object. Hotter things emit more energy, but also generally higher frequency energy. Okay? Now, you are made up of a lot of different materials, mostly water, but other things too. But these radiation signatures are characteristic of solids, liquids, and very dense gases. Those usually emit black body radiation. But if you take lighter weight gases, less dense gases, and heat them up, typically you're going to get emissions at very characteristic frequencies. Not at some continuous distribution, but at very characteristic frequencies. Now, if it's diffuse matter, meaning you have a lot of different material in there, you'll get these incandescent gases. Boy, they're leaving out a lot. You're going to have to read the book and fill in the gaps here. Well, it can. If you heat it up, they do. Well, the gases in this. Actually, you're not even heating them. You're just energizing them for those ions flying back and forth up and down the tube. That's energizing the gases that are in there, okay, and giving off light. So those are incandescent gases. So if you heat things up enough or add enough energy to them, some things will start, especially the lighter weight gas, will start emitting the spectrum. You might not pick it up, but if you have sensitive enough material, you can. So here's an illustration of it. They call it the Balmer series, because some guy named Balmer, well, no, this isn't quite here yet. Here, if we have Basically, this is an incandescent bulb. It has a titanium, probably, or some type of filament in it. It's heating up to a very high temperature, and it's giving off a spectrum of light. Now, depending on the material that's in there and the gas that's in there, they try to get it as close as they can to white light. And if you've noticed bulbs that you buy, some of them are sort of bluish tinged, some of them are yellowish, and some of them are whitish. And they do this especially now with the LED bulbs. You can pick your spectrum that you want. Okay, what they do, they have a light source here. It could be the sun, it could be a bulb, it could be anything that you've got here that's producing light. You have a slit that basically gets it into a column, so you have this band of white light coming through here. You hit the edge of a prism, which is a dense glass here, and because the low energy light gets bent more than the high energy light, okay, and it actually gets bent twice, once going in and once coming out, then you get the spectrum of light. Red, orange, yellow, green, blue, and some people put indigo in there in between blue and violet, and then violet. The indigo would be something in there. Really, the only reason I put it in there is so it would make an acronym. Roy G, this would be Roy, they put indigo in there, Roy G. Biv, okay? It really is a separate color, but they usually do. Okay, the closer you are to natural white light, the closer you're going to get to that spectrum. Because that's the spectrum that the sun is emitting, or at least that's getting filtered through our atmosphere that the sun is emitting, okay? That portion that's coming through. An incandescent bulb most of the time is going to be a bit yellow or an orange, so these will be thicker, those will be thinner. They have a variety of fluorescence too. Some are very whitish, and some are yellowish, and some are bluish. That just depends on which ones of these are thicker. Okay, so that's your diffuse spectrum. Okay, if you had a trying to figure out what they're showing, this as looks like a fluorescent tube. My guess is what they're meaning. This is a what's that? Yeah, it's filled with one special gas, like a neon bulb or something like that. Okay, and then you would do it and send it through that same prism. You get distinctly different lines. An orangey up here, a blue, a violet, and I don't know what color that's supposed to be. Maybe that's ultraviolet. I don't know. But anyway, you begin to get for diffuse matter. A broad spectrum is what you usually get for liquids, dense gases, solids, and stuff. But when you have an individual gas like neon or some of the other, almost your laser type stuff, it's not quite the same as a laser, but sort of like that, then you get very distinctly different lines of color. And I really find this book's description of this to be a bit on the weak side. But when you get much more complicated, the math gets really bad. So trying to keep it at this level, you might say. Okay. So Niels Bohr, a Danish physicist, came along. He was followed basically in time shortly after, they lived all at the same time, Max Planck, Einstein, Niels Bohr. One of the things Niels Bohr did, he came up with this theory of the hydrogen atom. How in the world is it going to, what makes it what it is? And, frankly, you go back here, I thought there was something else. Looking at this, we are running short of time. I think we better start Bohr's theory next time. So basically this is going to be starting, even though we've already hit some of the quantum concept, we're going back and picking up Bohr's theory here. So I'm going, here we go. Whoa, before we do that, there are some really good slides that this book isn't listing. And one of these is also example 8.3. So basically, that's what I was looking for. I thought it mentioned the Balmer series here. There it is. The line spectrum from the Balmer series. It was on the slide. Here's where I think it belonged. We had that slide, then that slide, and then no slide. My guess that was figure 8.9. So let's go back. The slides in the book aren't tying together. We'll start with Bohr's theory, but we're going to back up and do some of these slides that we see here, and we'll do 18.3. Nope, I'm going to back off from that. We're going to start with the Balmer series. That was the last thing on the slide, but we don't have a slide to do it. So we're going to start next time with the Balmer series, okay? And then we'll pick up on Bohr's theory. This will be we'll go back to the slide and just do that last bit on Balmer series. Okay. Sorry about that. The slide set, I think, has just lost some slides somewhere in there, and it didn't come across well. So I'm going to pause this. I don't have that many. No. How many you really need to know? Okay.
Sounds good.
All right. All right. What we're going to do is I have a permanent magnet here. At least I hope it is. Okay. Now, I need a few people to test some materials. If you notice at the very beginning, the Roman numeral 1, answer 12 or more, even not. Don't worry with that. We're not doing that. That's from a previous book. Previous everything, so don't worry about that. We're starting with 2A. Here's a permanent magnet, okay? And I'll pass some things around, and you pass the magnet around.
Must be aluminum.
More beside you. And here. Oh, can you? Okay, I'm going to give you styrofoam then, okay? You're going to have to test it for me, okay? We'll see. Okay, look at that. Exactly the right number. Okay. All right, wait. Let's not get too far ahead of ourselves. All right. So, Camp has the magnet, and he has what?
Aluminum.
Aluminum. Does it stick?
No.
Okay. Pass it. Okay. Everybody hear that? No. Even though the aluminum is nice looking metal, not sticking. And he's checking to make sure it is a magnet. It seems to be, right?
It's a magnet.
Okay. How about copper? James has copper?
No.
Nope, no on copper. As Mason, you got iron?
Copper is Cu, ain't it?
Yeah, Cu. Aluminum's Al, copper Cu. And you put wire in in the blank. Okay. You got iron? What you say? Definitely. So iron is a yes. Okay. Behind you, I think Samuel has. What do you have? Lead?
Yes.
Okay. PB lead? What you say? Nope. Pass it on down. Look at that. Nickel, it sticks. So yes, nickel's a yes. How about tin? It looks a lot like nickel. What do you think? Nope. Okay. How about zinc? Huh? SN is tin. Stannous, as in stannous fluoride. Okay. Nope. Zinc is a no too. And then, oh, I got the order in the wrong place. Somebody back there has plastic. Charles is going to do styrofoam first.
That's sticks.
Yeah, right. Okay. That's a no on styrofoam.
For sure the rest of it.
What you got?
I got wood.
Wood? What do you say about wood? Nope. Okay. How about plastic?
Come on, plastic.
Nope. No on plastic. That was pretty hard, wasn't it?
It will stick
Okay.
to a phone screen, though.
What's that?
It will stick to a phone screen. You know,
A what kind of screen?
phone screen.
Oh, I bet so, and it might mess up your electronics too.
No,
Oh, it won't?
never.
Good.
Why ain't you got no cobalt in here?
Okay, I'll take up the materials and
You got no dime under there?
the diamond.
Yeah.
I had some, but my wife took them all, I think. Okay.
Why ain't you got no cobalt?
Don't know. They didn't provide any. It's a fairly rare, so it probably would be too expensive. Here, Samuel is bending my lead like crazy.
There's one in the parking lot. Cobalt.
Okay. Huh?
There's cobalt in the parking lot.
Should be cool.
Okay. 3 more. Thank you much. All right. First part was pretty hard, wasn't it?
Oh, yeah.
This is the hardest one yet.
Well, I'll see if I can.
Next part. Need a volunteer?
What's up? Okay.
Okay. Here's some iron filings. Please don't drop them and spill them anywhere. They're a mess to clean up. Now here I have a needle of some sort, a pin. Let's stick it in the iron filings to see if it's magnetized much. I think it will be a little bit, but maybe not too much. Just a little bit. Okay. Wow, I just tried it and it wasn't that much. I don't know why.
Maybe stick to it.
Okay, turn it around and try the head too and see if it's magnetized.
How you know we didn't know the side?
Okay, we're going to have to determine that. What you say? A little bit, but not much.
Yeah.
All my pens, I've used them so many years, they've all been magnetized one time or another. So, now, let's do another one. That
Go ahead and
is,
drink it. Go ahead and drink it. If you're curious, drink it. See what it tastes like there.
It's in a Pepsi thing, so it can't be that harmful.
okay, now keep these separate. That's the one that's not very much, right?
Yes, sir.
Try this one and see. Is it more or less?
Say more.
More, okay. So that one's more magnetized. Now, you might wonder why I have,
What do you put the magnet on?
Yeah, it's in a cup full of metal shavings.
because I had a lot of people making a big mess, decided not to do it in a pool of container of water, but I've got a compass here, okay? Now, I won't count. Y'all can gather around. I think it would be helpful for y'all to gather around so you can see it. Okay? Okay. Now what we're trying to do, this is the one that was more magnetized. Okay? He's playing with the big compass. Okay. Now, y'all gathered around, you can see. Now, Camp's going to test this to see which is the north-seeking and which is the south-seeking end of that pin. And by the way, did you try the head too, or did you only try the point? Oh, lots of filings, right? Now, how can you tell which is the north-seeking and which is south-seeking if we're not putting it in the pool of water? Hint. I've got a map compass here. Okay.
The compass gonna
How will it tell you?
compass gonna
Go
point to
away
the
from
north.
the north.
Okay, I've got it pointing to the north.
Put the
Take this and put it close to which?
pick either end and see what happens. Move it over to the side.
Yeah, slightly one-sided. Ah, what's it doing?
repelling that.
It's repelling it, so the point must be the north-seeking. Okay, try the other one.
So we're going to just point right here.
What's that doing?
Following.
It's attracting it. So what does that mean the head is? South-seeking. Okay, so y'all got it? Number B1,
North is
the point was the north-seeking, and the head was the south-seeking. Okay, done that part. Second part, this was the one that wasn't very magnetized, right?
Yes, sir.
Okay. Now what I want you to do is stroke that on one or the other ends of this. Just do it in sort of the same direction over and over. Stroke it several times. Y'all see what he's doing? Okay. Now, stick it into your iron file. What would you say? Hey! He must have been holding his mouth a certain way. You know, he got it all to be magnetized. Now, he only stroked the point. Okay? So, try flipping it over. Remember, the head wasn't magnetized either, was it? Okay? Try that. Oh!
You can't magnetize one without the other.
Absolutely. Okay, so the question is, did you magnetize the head as well? Yes or no?
Yes.
Yes. And if yes, explain how you increase the magnetism of the head by stroking only the point.
You can't do one without the other.
Why?
You can't have a North Pole without a South.
Just gonna put you can't do
What?
one without the other.
Yeah. All magnets are always
Magnetizing.
Polar.
dipoles. They always have two poles. You'll never find a magnetic monopole. Or if you do, you win the Nobel Prize or something like that. Okay. So, magnets are always dipoles, not dipoles. Okay. Now, let's see which of those points. That's the one you just made, right?
Yes, sir.
Okay, we need to find out whether what's north and south. Whoa! What would you say?
Out there's gonna be north.
And which is that?
The point.
The point looks like a north-seeking, and yeah, the south is definitely the head is definitely a south-seeking. Okay, why was that true? He happened to have been stroking on the north end of the bar magnet.
So what
Okay.
happens if I was to take the north end now and strike it on the south side?
Okay, try it. Good question.
It's going to stick. You can start a fire now.
Okay, now stick it in the file.
It's still magnetized.
Okay. And that's the point. And the point was what before? Look at it now. He just made it a south-seeking. Okay? That's what happens. Now, I don't know how many, but probably just a couple, about half as many strokes as you had done. If you had tried it then, it probably would have been fairly demagnetized, because you have to change the magnetism. Maybe one stroke would have demagnetized it. I don't know. Nope.
No.
Okay, are you doing north or south? North? Okay.
What's with the styrofoam?
Okay. It's going to be hard to say. Maybe just the most recent will automatically do it.
Did you
Okay.
shake your head in the cook?
There.
Where's styrofoam right now?
Oh, so when I put it in water, it would float. Before I put it in a pool of water and we saw which way it pointed.
How long
I
did it
just-
take you to figure that out?
Huh?
How long did it take you to figure that out? You need some styrofoam.
I didn't. It didn't take long. I didn't try it.
What
Okay.
you say you had in that cup right there?
Okay.
Metal file.
Everybody got that?
Metal
Okay.
file. I ain't gonna do what you said.
What was it now?
I was asking what you had in the cup.
Oh, iron filings.
265.
Iron filings.
Those are the metal filing cabinet. I guess it's
Okay, that's where we're going next. Okay?
Filings come from? That's where all these filings come from, the filing cabinet?
No, okay. This was here when I got here, so I've been using them ever since. Okay. Y'all got number 4 answered, right? Now we're not going to 265 because, say again?
You said that wrong block?
Yeah, because I don't have a metal file cabinet in there. I used to, but not anymore. So we're going to the records office, okay? And we're going to take our magnet, and that's all we need to take in your lab. So bring something to write with, and you can leave you don't need the magnet if you don't want to take it. Oh, you want to take it? Okay. Okay.
Hey, if they're both like north, or one of them's north and one of them's south, why are they both sticking to it?
Because the magnet is so much stronger. See, that's repelling, right?
Oh, okay.
But you get too close and it overpowers.
Okay, that's their sign.
Duh.
That's the
See, that attracts. No?
We gonna skip all the ones about the nail?
Just those two, 9 and 10. 11 we can answer. Okay? Explain how you made a magnet without stroking another magnet. The
By
file
whooping
cabinet.
it.
Huh?
By whooping it. By beating
Okay. It was by,
it.
yes, by perturbing is the word I like to use. The Perturbing.
That's a capital P?
Huh? It's disrupting this, the domains, the naturally occurring domains. That filing cabinet, by the way, was mostly iron. And by disturbing the domains of that, by opening and closing the drawers, you, in the presence of the Earth's magnetic field, you made them line up and become a magnet. Yes?
Perturbing the what?
A magnetic material in the presence of a magnetic field. This is 11, huh? Explain how you made a magnet without stroking another magnet. And Camp said he didn't go in there and stroke the filing cabinet, so I believe him, I guess. Huh? Yes, because it got disturbed in the presence of the Earth's magnetic field. Exactly. All right. Now, I've got a little more setup to do. I just wanted to get started.
You about to make an electromagnet?
Yeah, we're going to do some electromagnetism.
You got a battery and some wire?
What's that?
You got a battery and some wire?
I'm not going to use battery. This is a lot better. Batteries run out so quickly and get weak so fast.
Still can't.
This is right up here.
We don't work on Toyotas.
They donated it to us.
We don't mess with Toyotas, man. I'm sorry.
You went to skip this.
You got no Chevrolet or what?
They didn't donate it.
No, man, transmission's no up.
Okay. Let me get. Let's see. These don't work.
So we all y'all drive Ford?
No, I'll make one of the ones that don't.
Did you buy Ford?
Do I buy for it? Oh, I have 10 of them.
Huh?
I have 10 of them.
No, none of them work.
Oh, the Ford program doesn't provide y'all cars? Never mind.
What? This ain't Harvard?
He opened his up. When you say he had 10 of them, that means 9 of them broke out.
Pretty much.
Your ratio is wrong. My Chevrolet
The
broke.
other 9
Yeah,
were parts for the one that's running.
Okay.
I got one.
All right.
One of them is people.
Now, this is going to be a little touchy because there's so many magnets on this board. Okay? But I'm going to try my best to get it set up so you can tell a difference. Okay?
What you know, electromagnet?
We're going to make one.
So you're gonna go up there and watch you or what?
All right. This is a little unfortunate because it's already facing almost. Okay. So y'all need to come up and gather around. Come up here.
Gather around the campfire and sing the campfire song.
All right. Now you'll notice here we're going to increase the voltage on this, and I want y'all to be looking at the compass needle to see if anything happens. So get close enough you can see that. I'll get over here. So y'all can see the compass needle. plenty of room over there.
Yeah, fine, no problem.
Series of magnets.
Some electromagnetism.
Okay, can y'all see? Move over there. Move over there. Move on down. Okay.
No, I can't see.
Oh, we don't care what
Okay, y'all are looking at the compass needle here. Okay? Now what I've got is red to red, red to red, black to black, black to black. Okay? Now, let's see if I can make the compass needle move by increasing the voltage here. Which way is it moving? Toward the end of the magnet or away from it? I mean the coil. Yeah, it is because it's pointing so closely to it.
slide it down.
Really close enough to the
You see, if I get down here, I start getting that magnet. Okay,
all I'm gonna drive now?
let's see if this will work.
Or is it just that one magnet on the drive?
Just this one right here. Okay? Can y'all see? I'll try to get out of the way now. Maybe that. See if this does better.
Okay, so south is repelling.
Okay. So what happened, it says, plug the black wire in the black socket, red wire to the red socket, place a compass near the coil, touch the red wire to the positive end, and not a 1.5 volt battery. I made my own battery here. The black wire to the negative. What happens to the compass needle?
It repels, right?
What is repelled?
So,
The south pole of the compass is repelled from the left end of the coil, right?
South pole of the
Compass repelled by the left end of the coil. So which would you say is the north pole of the coil? The right. Very good. Because the left end repelled the south, that means the right end would be attracted. Okay, now, what we're going to do is reverse the polarity.
on reverse
What's that?
reverse.
Let's see. Ah, the south pole is now attracted to the left end. Okay? So the question is, are there changes? Yes. And you can write that in if you want to. All right, that was station A. We move to station B. Now this is going to take a bit of coordination here.
Yellow, Mike.
What's that?
Yellow.
All right. Now what I want someone to do is turn off the light back there.
Left and what, in here?
Yeah. And let's turn off the light over here. All right. Now, at station B, plug the wires according to the colors, including two yellow ones from positions 2 here to whatever that is there, 14, below the microammeter. Now, one person is going to hold, I'm going to crank this up to 9 volts. Okay, I may have to even go higher. And what I'm going to do, I'm going to connect and disconnect. Okay? And what I want you to do, one person is going to look at these lights here. There's a red and a green. And you tell me if either light comes on when I connect and when I disconnect. Now, the first part here is on connecting. So don't put anything down for disconnecting. Only when I say connect, you tell me what's happening. Now, can any of you see the micro M meter? You can? Can you see, you think if it moves it? It's not moving now, but you think you'll be able to tell any movement with it this dark. Okay, so one person, at least some of you look at the lights here, and some of you look at the micro M meter. Okay? Now, I'm going to crank this up to at least 9 volts. Okay. Okay. Now, when I connect, do you tell me what you see on the light and the microammeter? Connect? Did you see anything? No. Nothing at all. No light came on? Oh, I'm sorry. I put it on the wrong one. Yeah. I wasn't paying attention. Okay, let's try it again. Look at the, what's that? Okay. That does tend to come up. So, someone, let me do this. This will be like connect or disconnect. That connection, disconnect really easy. Okay. So, somebody look at microammeter? Someone looking at the lights. Okay? This is going to be a connect. Did anything happen?
Yeah, the amp was just a little bit.
Okay. Did the lights do anything?
The voltage dropped.
Okay. Did the lights do anything? Nothing at all.
No.
Let me try again. Connect. No light. Disconnect. Okay. Okay, let me turn it up a little. Look at the lights. Connect. No light. Disconnect. Okay. Look for connect now. Connect. Which light? Red light? Okay. Did you see the microammeter move at all? Which way?
Looked on red and first put on there, went to positive.
Went to positive. Okay, got that one now finally.
Connect was green.
Okay. Record what happens to the light and ammeter. Which light came on connect? Red. And what happened to the ammeter?
Went positive.
Went to positive. Okay, this is number C4. That's an explosive. Okay.
You mean, yeah, I see.
The light went red and the ammeter went positive. Okay? Now, I'm going to disconnect, so I want y'all to be watching too, but I want to wait until you're ready. And then, it did? All right, they already noticed that. Okay, when disconnected, the green light came on and the ammeter went negative, correct? Okay. Now, what I'm going to do is swap polarity. From black to red. Okay, we'll see if it does. Okay? What happens to the lights when I connect? You ready to watch? Okay? Connect. Okay, let me try it again. Okay? Ready? Connect. Green light,
Green light went negative.
and it went negative. Microammeter went negative.
Versus.
Huh? Yes.
Versus.
Well, let's, yeah. Okay, y'all got that?
You working on?
This is C6 was green light came on connection and ammeter went negative. Okay, that's fine.
I put same
Okay.
as number 5. What if I do that?
Okay, that would work too. Okay, what happens to disconnect? Are y'all watching? Okay, now I'm going to connect now. Okay, it's connected. Disconnect. Red and positive. Very good. Now, yeah. Ooh. It says explain these observations. Okay, now, can anyone tell me what those red and green lights are? Any guesses? Huh? They light. Okay.
Positive, negative,
They happen to be,
is that DC you putting in there or what?
yeah, DC. They happen to be, yeah, and they like diodes.
Yeah,
They only come on when the light goes in one direction or the other. And that's why. Now, when you saw two, that's because this thing, it touched and got off, yeah, it connected and disconnected. Okay. So what happens is, what's happening here? Now notice, here's the thing, folks. The current was going through this coil. That's connected here. There is no current going through this coil. So why were you getting lights and current when I disconnected and connected? Okay, very good. And by the way, when they were permanently connected, was it lit up then? No, it's only on connection and disconnection. Okay?
That's when you get your sudden burst.
Yeah, that's when you get a changing electric field through here, which produces a changing magnetic field here. That's what produces a current. A changing magnetic field is what produces a current. Not a constant magnetic field, that doesn't. The changing magnetic field. That's why it only happened on connection and disconnecting. And the reason it reversed was you were having the current go in the opposite direction here, so it reversed the polarity of your, basically that's like a solenoid. Okay?
So what you took the number 8, you got,
Okay?
you put about 4 or 5 words.
Okay. Only a changing magnetic field will produce an electric current.
Changing magnetic field.
Only a changing magnetic field produces an electric current.
Changing magnetic field.
Produce an electric current. Strong magnetic field doesn't produce an electric current unless it's a changing magnetic field. Okay. By the way, before y'all saw the things, I'd gotten up to about 11 volts on that one, so you can change that to 9 if you. It was saying 9, I did 11. So I'm going to crank this down and try to do this at 2.5. It may not work, but we'll do our best.
What else you want to do?
You could again too.
How do you do that?
Oh yeah, I guess.
Now you can do it.
This thing is nuts.
Shake the dial that you turn. Then you get whatever you want.
Turn like wide open for all, man.
Okay. If I have it over here, it's more responsive. Okay.
Leave it alone, leave it alone. Don't touch it.
That's close to 2.5, 2.6. Okay.
No, it says 1.5.
Okay. We'll go with it. Okay. Sorry about that. Okay. We did 11 on the other one. It said 9. Okay. Now notice what the deal is up here, though. What has changed here? Okay. All right. So, putting a smaller battery in, somebody look at the lights and someone look at the ammeter. You looking?
Look.
Someone look at lights? Okay. Connect. Disconnect.
Red went positive.
Okay. On connection, it went red and positive. On disconnection, it went green and negative. Is that right? Okay. Now, just a dumb question here. Was the light more noticeable or less? Way more? Okay, how about the ammeter?
Yes, more.
Real? Okay, more. Even though we had less voltage. Wow. Okay. What's that? Okay. Now, that was what, number 9, right? Let's do the 10. Maybe I should have done 1.5. Okay. I'm going to reverse the polarity here. Y'all ready? Okay.
Ready.
Connect. Disconnect. Connect. Disconnect. Now what about the ammeter?
Yeah, just the reverse.
Okay. So it reversed again. Okay. Record the responses on connecting and
Everything
disconnecting.
reversed.
Yeah. Okay. Now here's the big question. Number 11. Why were the responses greater at station C, which had a much smaller battery than B? This one was at 2.5, not 3.1. The other one's at 11. And yet you had greater response here than you did here.
Because the
Coil was shorter. Why do short, fat coils do more?
Just the number
Only
of
got one
turns.
coil.
Okay. What's that? Okay, now I think you're getting close. Where is this coil? It's inside the other coil.
I was gonna say.
Oh, okay, I thought you saw me do it.
No, I couldn't.
This coil, the supply coil, was inside the other coil. So what was the difference here? More of the field lines were being cut. In fact, almost all of them were being cut. Here, only the edge field lines were being cut. These, all the field lines. So it's not just, the changing field, it's how many field lines are being cut and changed. So that's the answer for 11. Because the coil on station C was inside the induced coil, you might say, the more field lines were being cut. Okay, I think I'm through with this. Turn that one off.
Station F. Wow.
Okay. Now I think we can turn on the light. Woo, right. Okay, Charles got to wake up now. Okay. Now.
Put the yellow ones in.
I did. I put them where I need. Okay. Now what we have here at station F, plug two sets of yellow wires in the terminals 8 and into 14. Okay. Now one person should turn the coil clockwise. Here's the coil, and you know which way clockwise is, right? Okay. That way. Okay. He's going to turn it clockwise. The others read the ammeter. What happens to it? Going positive. Right? Okay? The ammeter goes positive. There are no lights on this one, that's why we can turn on the lights. Okay? Now turn it counterclockwise. It goes negative. Ammeter goes negative. Now we're going to reverse the wires. Okay. Someone else want to go clockwise?
You reverse the wires on the coil or what?
Yeah, going from the coil.
You change your polarity.
Yeah, exactly. And it went opposite. First, when clockwise went negative and counterclockwise went positive.
So now it's going negative first when you reverse.
Yeah, yeah. Negative was clockwise, and is that right? Y'all were telling me.
What kind of connection is this?
Okay. What kind of connection is this? If everybody can come look. No, right here. Look at this connection. Notice that for half of this turn, this one is connected to one side and that one connected to the other. But as soon as you go past horizontal there, then they reverse sides. Right. And therefore, yeah, and you have a DC motor. Because as soon when you are cutting more field lines this way, you see you got a permanent north magnet here, a permanent south magnet here, so you have a strong magnetic field this way. And by turning this, you're cutting those field lines with your coil. So the more field lines you're cutting, like you did here, the stronger the field, the fewer that's being cut, the weaker the field, and every time you go to change that half a turn, it reverses coil. So that gives you, what kind of connection do you call this? That ring is split. A split ring.
Connection.
Y'all paid a lot of attention, didn't you? Commutator. It used to be what was in alternators before they started using dual or triple diodes, right? What's that?
Why do you give us on these plates like that? More like that big word.
Because I wanted to get it all on 3 pieces of paper.
What question you answering with that?
You can spill over if you want. It's called a split ring commutator. What's the reason?
Question what?
That's 14, the first part. See, there's an answer, comma, and then a longer answer. Okay. Yeah, you have to write an essay on that section. By the way, I was expecting to be flooded with papers today. Why am I disappointed? Oh, never mind.
You owe me $1.
All right.
I got a print.
You can ask this Duncan why I'm not, because I've been writing essays.
Well, then you should be good at it by now.
Adding one more to the yin yang.
All right. What is the result of having the commutator there? DC current, exactly. Every time it went to alternate, you might say, it reversed polarity, so it kept being. And didn't you notice it was sort of a pulse DC? It wasn't steady DC, but it was pulsed, right? Okay. Now let's go to station G. Here's station G. Now, someone tell me some differences between F and G. Here was F, and there's G.
There's more cold.
One of them got a stationary coil.
Okay, one has a stationary coil,
And a permanent
but a
magnet.
moving magnet. This has a
Permanent magnet.
and a
Stationary
moving
magnet.
coil. Exactly. Is that going to make any difference?
Oh, yes.
Oh, no.
No, it's going to operate the same.
Yeah, and here's why. It's all it takes is changing magnetic field lines. It doesn't matter whether it's because the coil is moving or the magnet's moving. All that matters is that you have something moving relative to the other.
If it don't matter, like, how come you spin that as fast as you can, it barely moves, you spin that one like crazy, it's going crazy.
And what does it do?
It's
Negative and
it's
positive.
like an AC
And what?
motor.
That is an AC motor. It's not because of the battery in the thing. It's because this hasn't got a commutator on it.
The
A commutator is
DC
what
motor
makes it.
got brushes on it.
Right.
That one don't need.
This will be what they call a brush.
And that would be an AC. Yeah.
Right. AC brush. This would be.
DC
I would call
motor.
these here is what I would call a brush.
Yeah, exactly.
Yeah, you call them split ring commutator.
Yeah, well,
I
yeah.
simply call them brush.
Well, the brushes are typically what these things are on either side. Yeah, that's what makes the contact.
So basically, a brush on the DC brush.
Like you take your alternator to the store to get it replaced, they're gonna change the brushes.
Right.
Give you a brand new.
No, they're
Alternator
gonna.
won't have
If they're gonna send it out.
The old
Nobody
Yeah,
gonna-
they're
Not me.
AC.
Huh?
They're AC and they can start.
Yeah, that's what does the conversion.
That's what I'm saying. They-
Yeah. Okay. Lab any good?
Yep.
Okay. When you get through with it?
Station G, what?
Oh yeah, okay, wait, I forgot. Okay. Okay, at station G, what was the responses to the ammeter? Did y'all get that somewhere? You can see it somewhere, you may not have.
Yeah, it went crazy.
Say again? No, AC. On G, the ammeter went both directions.
Wait now, which one?
15.
15.
15 was
Went
DC.
negative and
Huh?
No, on 15, number 15 was DC current, because I was right here.
No. 15 is on station G.
you gotta reach.
14 was the split ring commutator,
Yeah, which
and that made DC current. Okay. 14 was the first part, the little blank is split ring commutator, and the result of that was a DC current. You can call it pulse DC if you want to, but you don't have to. Okay. Now, on G, when we move to G, turn the thing, and what happens? It goes, yeah, the alternator, the ammeter goes positive and negative, indicating you're creating AC. Okay? Now, then 16, what differences do you see from those in station F? What differences do you see from G from F? Yeah, and why is that? F had the commutator
Yeah, F is DC.
because it had the commutator. G didn't have any commutation. So, what difference did you see? F was DC, G was AC. Why? Because F had a commutator, G did not. Make sense? Yes. Calculate the slope. What's that?
I'm good.
All right. Of the court. We call it the solenoid if you want to call it.
Hey, you gonna hook my current to them, let them things spin?
What's that?
You gonna hook my electricity to it, let it spin?
Hang on, I didn't hear the first one.
Hook up electricity to it.
It won't do it, we don't have, it's not, I don't wanna fire it up that way. Now, let's talk about, since everybody wasn't here at the very beginning, remember what we're gonna do from here on. Please do your student course evaluations if you haven't already. Okay. Next, on Thursday, we'll continue chapter 8 in class. If we finish chapter 8 before 2 hours, then we will even have time to do the lab for 8. I don't think we will. It's a pretty long chapter. Okay? If we don't finish chapter 8 in 2 hours, we'll keep doing it until we either finish chapter 8 or get to the last 30 minutes. Because the last 30 minutes of Thursday is going to be the chapter 6 test. Okay? Now my guess is then on Tuesday of next week, we will finish chapter 8. If we didn't, I think we will already have finished it. We'll do the lab for chapter 8. In fact, I may even give you the lab to take home over the weekend because it's nothing you do like this board. You just read the book and answer the questions. Okay, so you will be able to take that home. That way we can save on some lab time. But you don't have to. You can do it when we get back and we'll go over all that. Okay? And then, if we have finished it by Thursday, that means we can have the test on chapter 8 on Tuesday. Okay? Once we finish the lab on chapter 8 and the test on chapter 8, that's all we have to do on Tuesday. If you want to go on and take the final exam Tuesday, you can. If you'd rather wait till Thursday, I'll be here all day Thursday. Okay?
Where you want us to put these?
I'll take it. You finished? Okay. Any questions? I don't know. Let me see. Let's see. Oh, I got it.
You have it?
Yep.
Snuck into the radar.
Okay. Good deal. Sorry I cheated you out of your tuition dollars.
It's all good, man. We're gonna let this one slide.
What's that?
We're gonna let this one slide.
Who is this? Atlanta Hawks? What's this? Atlanta Hawks or what?
Oh, no,
Braves.
Braves.
Oh, baseball. Okay. I see. Go Braves.
Right.
Okay.